think now we can pass to the very last keynote speaker of this workshop, that is Dr. Matteo Gatti. It's my real pleasure to have Matteo over. So Matteo is from French CNRS in Paris, Palaiseau, and also Soleil synchrotron, if I'm not wrong. And Matteo is an expert of many-body perturbation theory and I would say theoretical spectroscopy in general. And that is also the idea of having him over, since today we've been looking at methods aimed at describing spectral properties. We also wanted to have a wider view on the field of theoretical spectroscopy. And today Matteo is going to talk about design of auxiliary systems and connectors for spectroscopy. So Matteo, please, the stage is yours. Please. Thank you very much, Andrea, for the kind introduction. Good evening. I guess I should say good evening, good morning, or good night, depending where you are. And thank you very much for being here until the very end of this very nice and stimulating tutorial. Many thanks to the organizers for this invitation. And as a participant of the tutorial, I've learned many things myself. Let me try to share presentation. Okay. Do you see it? Everything is okay?
Yes, all good.
Yes, we can.
Okay, all right. So we can start. The goal of my seminar will be to place different frameworks, namely density functional theory, Green's function theory, the spectral potential within a common perspective. And to do so, I will introduce a common strategy, which is the design of auxiliary systems that are characterized by potential or kernels that have the property to target only specific observables. I will then suggest the connector theory as a systematic strategy for approximation. And if time permits, towards the end, I will advocate a new ecological approach for materials design that is based on these concepts. Okay, I think this is one of the most important slides of my presentation. And since I have the risk to run late, out of time, let's say, I would like, first of all, to thank all the people that have contributed to this work. What I'm going to tell you, I've learned mostly from them. So I would like to thank Marco, Ayub, Martin, Jaco, Lucia, and other members of the theoretical spectroscopy group in Palaiseau and friends of the group. So many thanks to them. We'll start with something that we are all familiar with, which is quantum mechanics. We know from quantum mechanics that if we solve the many-body Schrödinger equation, we can calculate and we can obtain the many-body wave function. And from the many-body wave function, simply calculating expectation values of appropriate operators, we can get, in principle, all the observables. Now, the point is that, in general, we are not interested in getting all the observables, all the possible observables. In general, instead, we are interested in a limited answer to specific questions. In particular, in the case of DFT, we are interested in the ground state density. We are not interested in the calculation of the many-body wave function. And if you are interested just in the ground state density, Kohn and Sham have proposed the idea of introducing an auxiliary world, an auxiliary system of independent particles that are the Kohn-Sham particles. This Kohn-Sham system is meant to give us the ground state density, but not, for example, the many-body wave function. Indeed, these Kohn-Sham particles are living in a completely different universe. They are independent particles, and they are not embedded in the external potential of the original Hamiltonian, but they are embedded in the Kohn-Sham potential, which is an effective potential, and a part of this potential, which is the exchange and correlation part, is unknown. So this is not the end of the story. And indeed, Kohn and Sham have also proposed to introduce a third universe, which is a model universe that is in this case, the homogeneous electron gas that is characterized by the same density, the homogeneous density everywhere. In this model world, we can calculate the exchange and correlation potential, which is this exchange and correlation potential of this homogeneous electron gas. And then the idea of Kohn and Sham is to connect the model world and the auxiliary world in such a way that we can obtain the exchange and correlation potential from the homogeneous electron gas. And this is the idea of the local density approximation. It's an approximation because it's telling us that in order to obtain the exchange and correlation potential at the point R, we have to consider the density of the homogeneous electron gas that is equal to the local density. So in this way, we establish a connection between the model world and the auxiliary world. And at the end, we can obtain the observable of interest that is, in this case, the ground state density. This is a very successful framework. And that's the basis of all the DFT calculations that we are doing nowadays. Now, why this is working so well? Well, the first big advantage of this idea is that it's much easier to use this model world, the homogeneous electron gas, to approximate the effective potential, and in particular, just a part of it, of the auxiliary system, rather than approximating the real system directly. We don't use the homogeneous electron gas to approximate the real system. We use the homogeneous electron gas to calculate a small part of the effective potential of the auxiliary system. This is the first advantage. The second big advantage is that the difficulty calculation in the model has been done once and forever. And this hard task has been done by someone else. And so we profit from the work that has been done by Seperli and Alder that have calculated using accurate quantum Monte Carlo approaches the exchange and correlation potential of the homogeneous electron gas. The big advantage is that now we can just import this information from the model, and we don't have to recalculate this every time we do an LDA calculation or a DFT calculation. This is very important. It's why we can do LDA calculation in practice. Otherwise, the cost would be too expensive. Now, an important remark, I think, is that, of course, in exact DFT, we get the exact ground state density and the exact ground state energy, total energy. But in approximate DFT, this is not true. We get an approximate density, which is the input of the functional, and we also approximate the form of the function. So at the end, we get an approximate total energy. But in principle, we make two different kinds of errors, an error on the density, on the input of the functional, and an error of the form of the functional. And these two kinds of errors have been actually analyzed in details by Kieron Burke and collaborators in a series of papers. So we can distinguish error in the densities and errors in the energy functional. So if you're interested, you can have a look at this reference and a series of other references. And moreover, in this article by John Perdue and co-workers, they've taken an historical perspective, and they've realized that in general, the approximations of DFT are biased towards obtaining good energies rather than good densities. So many times we develop functionals that are producing good energies, but not good densities. And the reason is because we are interested in having good energies. And this is also true in general in many quantum chemical applications. So we are biased towards finding good energies. More recently, in just last year, Si-Hwan Chen and collaborators in New York have done accurate quantum Monte Carlo calculations like the ones of Seperli and Alder, but in this case in real materials, not in the homogeneous electron gas. They have calculated the density, the ground state density, and they have compared the ground state density obtained from quantum Monte Carlo, from their calculations, to different flavors of the approximations of the functionals in DFT. And here it's a result for bulk silicon across a particular path in the unit cell. This is not relevant here. The important thing is that they have been able to compare different functionals with an accurate density that has been obtained, again, as I was saying, by quantum Monte Carlo. So we can compare in this way really the result of the functionals in terms of the density. Okay. Another important remark is the fact that the auxiliary system is supposed, the Consham system is supposed to give us the density, but it's not supposed to give us directly other observables of interest. In particular, the density functional of the observables of interest is often unknown. So we know the density, even if we know the density, very often we don't know the density functional to obtain the observable of interest. We know that the observable of interest can be obtained as a functional of the many-body wave function, but we don't calculate the many-body wave function using DFT. What we can calculate, what we obtain is the Consham many-body wave function that is a Slater determinant. And then very often we use the same functional form as the one that requires the many-body wave function with a Consham input. And of course, this is introducing an error. And this in particular is the reason why very often we obtain results using Consham that are not in agreement with the experiment. And this is in particular the case of the band gap of materials. How we can assess this kind of error? The point is that having the density calculated from quantum Monte Carlo, we can solve an inverse Consham problem. Namely, we can start from the density and obtain the exchange correlation potential, solving this inverse Consham problem. Normally, we start from an external potential, we have an exchange correlation approximation, and our target is the density. In this case, the density has been given by this accurate quantum Monte Carlo calculation, and we can reverse engineer the problem to obtain accurate exchange correlation potentials. Then we can compare the exchange correlation potential derived from quantum Monte Carlo to different approximations. But for the interest of time, I will skip this comparison and I will go directly to the fact that using this exchange correlation potential derived from quantum Monte Carlo, we can now solve the Consham problem exactly, or let's say very accurately. And we can compare the Consham gap obtained from quantum Monte Carlo with standard approximations like PBE and LDA. And in this table, we have a comparison of the indirect and direct gap at gamma for silicon, or the direct gap at gamma for sodium chloride, between quantum Monte Carlo, PBE, LDA, and the experiment, where the experiment is an experiment where we obtain the band gap combining direct and inverse photoemission. These gaps instead are Consham band gaps. And what you see is that actually PBE is an excellent approximation to the exact or to the very accurate Consham band gap that is obtained from quantum Monte Carlo. And also LDA is a very good approximation. And all of them, all these Consham gaps, are underestimating the experimental gap. This is confirming a conclusion that was already derived by Godby, Schluter, and Sham in the middle of the 80s, based on the GW approximation to the self-energy. In this case, instead, we start from a very accurate Consham Consham exchange correlation potential that is obtained from quantum Monte Carlo. So the message here is that we shouldn't blame the LDA or the PB in this case. The fact that the gap is underestimated, it's because the Consham gap is not supposed to give us the exact band gap that is measured in the experiment. And since there is a lot of confusion on this point, I would like to underline that several common DFT approximations like hybrid, scan, LDA plus U are actually not using a local multiplicative Consham potential, the one we are talking about now. they use a different kind of Constant potential. In particular, they can be framed in the framework of generalized Constant theory, where there is a non-local potential, a non-local Constant potential. And in this case, the band gap can be larger. Okay, so it's important to distinguish the fact that we use here, we consider a local multiplicative Constant potential. We can also say that sometimes we derive approximations that are tuned in such a way to give the good gaps, the gaps that are measured experimentally, like in the case of the modified Beckett-Johnson meta-GGA. And indeed, if you do the calculation in silicon, you obtain, for example, a direct band gap that is in good agreement with the experiment. But then if you compare the density that you obtain from this functional with respect to quantum Monte Carlo, the error is actually larger than in the case of LDA. And the final point is that in general, we would like to have more quantum Monte Carlo accurate benchmarks. So if you are a quantum Monte Carlo guy in the audience, you are very welcome to produce benchmarks that are very important for us. And I think it's much better to compare calculations with other accurate calculations with respect to the comparison with the experiment, because of course life is much more complicated, and experiments that are other effects that are not present in our calculations. Okay, so what we have already remarked is the fact that this framework that has been introduced by Conecham is a framework where we introduce different universes, and each of them has a different role, but it's very, very successful. And so the idea is that we can learn from this very successful suggestion of Conecham, and we can think about generalizing this scheme to other observables of interest. This would lead us to introduce different auxiliary words, or maybe other model words. And we can also think about generalizing the LDA idea of connecting model and auxiliary words. And this is what I will do in the following with the other approaches. And in particular, the first framework I would like to discuss is the one of Green's function theory. The Green's function is another reduced quantity. It's a quantity that always depends only on two space coordinate and one frequency, independently of the number of electrons. Like the density that is always depending on one coordinate independently of the number of electrons. That's why we call them reduced quantities. We can understand the Green's function that has been already introduced, by the way, this morning by Andrea Ferretti, as a dynamical density matrix, or alternatively as a propagator of one additional particle in the system. Why we use Green's functions? The reason is that we want to target spectral properties like additional removal energies, band gaps that are measured in photoemission, that are not known functionals of the density, but they are simple functionals of the one-body Green's function. So if you are able to calculate the Green's function, you have access directly to these properties, to the band structure, contrary to the case of Conecham and DFT. We can frame Green's function theory in the same way. In this case, we are not interested in the many-body wave function. We are just interested in the one-body Green's function. And we can think that we are, in this way, introducing an auxiliary word that is just targeting the observable, the quantity of interest. The Green's function per se is not an observable, but it's related to observables. And in this auxiliary word, there is an effective potential that is the self-energy, that is more complicated than the Conecham exchange and correlation potential, because it's non-local, it's frequency dependent, and it's complex. It's more complicated because the object of interest is also more complicated than the density. So also in this case, we have an auxiliary word. The difference is that usually, in the case of Green's function theory, when we have to introduce approximation, we use perturbation theory and or resummation techniques. For example, we use the GW approximation that is based on many-body perturbation theory to approximate the exchange and correlation part of the self-energy. This is very successful. This is the usual publicity slide where you see that the GW approximation of the self-energy is improving with respect to the LDA in the calculation of the band gaps. But still, the Grace function theory is much more expensive than Consham DFT. And the main reason is the fact that the self-energy is recalculated for each material, contrary to the LDA and Consham LDA, where we import some information from a model. In this case, we calculate the self-energy, calculating G and W each time we need to calculate a different material. So this is very costly. So how can we address this problem? We could take inspiration from LDA of Consham. So we could introduce a model word. In particular, we could introduce the homogeneous electron gas, where we have this homogeneous density and where the self-energy can be, in principle, calculated. Now, we immediately see that there is a problem if we want to design an LDA for the self-energy. The LDA is based on the fact that we need the density at a given point in order to define the object of interest. But in our case, the self-energy is dependent on two space points. So which energy should I take in order to do the LDA for the self-energy? And the other problem is the fact that the model, the homogeneous electron gas, is not known accurately. In the case of Consham DFT, Quantum Monte Carlo was able to calculate the exchange and correlation potential very accurately in the case of the homogeneous electron gas. Unfortunately, for frequency-dependent quantities like the self-energy, this is not possible nowadays with Quantum Monte Carlo. But let's focus on the first problem, on the fact that the self-energy is no local potential. Okay, so actually, this was already addressed in the third paper of the series of basic papers on DFT by Kohn-Sham in 66. So after the Kohn-Sham paper on LDA and the Kohn-Sham system, Sham and Kohn also thought about this issue concerning the self-energy and the possibility to import information from the homogeneous electron gas, and the question about deriving an LDA for the self-energy. How they did this in practice? Well, they immediately decided to approximate the self-energy in such a way that the self-energy is no more a non-local potential, but they decided to construct a potential that is local and frequency dependent, and this is the recipe. But this is an approximation to this self-energy that is useful because now this is just a multiplicative operator and it's local, so an LDA can be introduced. This idea has then been used in practice by, for example, Wang and Pickett in the 80s for calculating band structures of real materials like silicon. And this goes under the name of quasi-particle local density approximation. Now, this approach is not popular anymore, and it has been outseeded by GW calculations in real materials. But I think that now maybe it's time to revise this old idea and to take inspiration from these old ideas of Kohn and Sham. There is an alternative solution to this, and it's just the fact that we are not obliged to have a connection through the local density. And this has been discussed in the framework of connector theory that I will introduce in the following. And it's just the fact that we can generalize this idea of this connection between a model word to an auxiliary word by introducing a more complicated connection. I'm not going too much into the details of this possibility. I just want to tell you that nowadays it's also possible to do differently. If you want to know more about the concept of connecting non-local quantities from auxiliary systems and model systems, I invite you to read these reference where we have discussed this, for example, in the case of the density matrix, which is also a non-local object. Now, I would like instead to focus on the second problem of many-body perturbation theory, of Green's function theory, which is the fact that these calculations are very expensive, and very often we are not interested in the full Green's function. As we are not interested very often in the full details of the many-body wave function, we are not interested in the full details of the Green's function. Indeed, a quantity of interest for many purposes is the local spectral function. The local spectral function in the framework of DFT is also known as the local density of states. This is just a generalization to the many-body world in the case of interacting electrons. Why this quantity is interesting? Well, it can be measured by STM. And from this quantity, if we integrate with respect to the coordinate r, we can obtain the integrated spectral function that can be compared with the photoemission. So it gives us the electronic structure, the band gap. And if we integrate over the frequency up to the Fermi energy, we also obtain the density. So this quantity is very interesting. And it has been already introduced this morning by Andrea, and on the first day by Nicola Marzari as well. And normally we calculate this local spectral function starting from the Green's function. The Green's function is obtained by using this complex non-local and frequency object that is the self-energy. And then we calculate this Green's function. We take the diagonal and we take just the imaginary part of the diagonal. So we throw away a lot of information that we have calculated, and then we have access to this local spectral function. This is the standard way, and you see that it's a waste of computational time, of computational resources. And we would like to calculate directly this quantity without passing through the Green's function, in the same way that we calculate directly the density in Consham DFT. We don't go through the complicated Green's function or the many-body wave function. And indeed, this is possible. We can generalize the idea of Consham DFT. So in Consham, we have the exchange correlation potential that is local, that is real, and it's static. And with this Consham exchange correlation potential, we obtain directly the density. We have shown that with a spectral potential that is also local as the Consham DFT1, but it's frequency dependent like the self-energy, and is also real like Consham. So with this spectral potential, we can obtain directly the local spectral function. This is a generalization of Consham, and it's much simpler than the self-energy because it's local and real. How we have proved that this is possible? We have introduced a generalization of the Sham-Schulter equation that has been already mentioned again by Andrea this morning. And I would like to spend some words about this, because this is a very general way to introduce effective potentials and kernels for quantities of interest. So not only for this local spectral function, for this spectral potential, but it has validity that is very general. So let's think that we are interested in a quantity Q that is a part of the information that is carried by the Green's function. The only requirement is that this part of G should be a linear operation. For example, we can take the diagonal of the Green's function. The Green's function is the solution of the Dyson equation with the self-energy. And this is the standard way that we have to calculate this quantity of interest. But now we can suppose that we can obtain alternatively this quantity of interest from a different Green's function that I call G of Q. And you see that this is specific of the quantity of interest. That's why there is this Pedix Q. And this time, this G of Q is determined by solving this alternative Dyson equation, where instead of the self-energy, I have a simpler potential that I call V of Q. I can now combine these two Dyson equations into a single one that is connecting the full Green's function and the Green's function G of Q. Now I take the part of interest of the Green's function and of G of Q. These two are the same by definition. So if I take the part of interest of this entire equation, this term and this term exactly cancel out. They drop out from the equation. And the condition that I obtain is this one. And now I can solve for the potential, for the effective potential V of Q. That is the one that is supposed to give me G of Q and then the quantity of interest. So this is an effective potential that I want to be simpler than the original self-energy. And I have the freedom to make different ansatz for this effective potential. The important condition is that I have to find a solution of this equation. This is, as I was saying, it's a very general approach to design potential and kernels in different frameworks. Depending on the quantity of interest, this can be applied to different frameworks. It's not limited to the single particle Green's function. It's also it can be also used for the two particle Green's function or for the n particle Green's function in general. And indeed, we have applied it also to time-dependent density functional theory to design kernels in TDFT. If you are interested in the general idea of generalized Shamsuter equation, this is a good reference. Now, why the name generalized Shamsuter equation? Because this equation has been derived for the first time in the case of DFT by Sham and Schluter. And this applies to the calculation of the ground state density, that is a diagonal in space and time of the Green's function. So in this case, Q is the density, and the part of G is the diagonal of G in space and time. And then you can make an ansatz to this effective potential, that is the Kohn-Sham ansatz of the exchange correlation potential being real, static, and local. And if you make these ansatz, you find only a unique solution apart from a constant shift that is arbitrary. So in this way, you can obtain VXC exactly with starting from ingredients coming from many-body perturbation theory that are the self-energy and the many-body Green's function. In principle, this is an exact definition of the exchange correlation potential. Note that this is not the unique choice, the only choice that you can make for this V of Q. Indeed, you could also assume that V of Q is a static, non-local real potential. And in this case, you would find that you can obtain many different solutions. So this is indeed the choice that is made in the case of generalized Kohn-Sham, where you make the choice of using a non-local V of Q such that the density is reproduced. So this is completely general, and the ansatz is something that you can choose with just the constraint that you should find a solution to this equation. And we have applied this same idea to the definition of the spectral potential for the calculation of the local spectral function, that is the diagonal in space of the imaginary part of the Green's function. And in this way, we have found that we need a potential that is frequency dependent in such a way to obtain this quantity of interest. A potential that is local but static, like Kohn-Sham, is not able to reproduce this quantity. You wouldn't find a solution to this equation. This is how we have introduced this spectral potential. In principle, this is exact if a solution to this equation can be found. Now, the important point I would like to make here is the fact that this spectral potential, which is supposed to give us exactly this quantity, the spectral function, is local, real, and dynamical. And I want to now stress the point that this spectral potential is real, contrary to the self-energy that is complex. And very often, the fact that the self-energy is complex is an important consequence of the interaction of between the electrons. It's also a fingerprint of dynamical correlation. So the question we can ask is, how is it possible that a real spectral potential is able to account for these effects of dynamical correlation that are related to the imaginary part of the self-energy? And we have studied this in a particular case, that is the Hubbard model in a Bethe lattice in infinite dimensions in an approximation that is the coherent potential approximation. We have done so because in this case, it's possible to have the self-energy analytical, and then we can solve this general Shanshütter equation, and we can construct this spectral potential exactly. And we can answer this question: how is it possible that this real spectral potential is able to obtain the same results as this frequency-dependent and complex self-energy? Why is this interesting? Because in this model is useful to study the Mott metal insulator transition that goes from a non-interacting case where you have a metal. This is the spectral function, the local spectral function. This is the Fermi energy. In the non-interacting case, you have a metal. And when you increase the Hubbard U, you go from a metal to an insulator. And this insulator is a Mott insulator because the metal insulator transition is driven by the fact that the self-energy, in particular the imaginary part of the self-energy, is becoming infinite. So in particular at this point, that is the point where the gap is opening, the imaginary part of the self-energy is not very clear, I have to admit, in this figure, but here it's becoming minus, the self-energy is becoming infinity. So this gap opening is related to the fact that the self-energy is diverging, and it's a fingerprint of the Mott metal insulator transition. Now, in our spectral potential, we don't have an imaginary part. So how is it possible that we are able to reproduce this metal insulator transition in a Mott insulator? Of course, in the case of Kohn-Sham DFT, this is not possible. In the case, so in Kohn-Sham DFT, we would simply obtain a metal in all the regimes. In the case of the spectral potential, this is possible, and it's possible because at the transition, the derivative of the spectral potential with respect to the frequency is diverging. So it's the role of the imaginary part of the self-energy is played by the derivative with respect to the frequency of the spectral potential. And in this way, the spectral potential is able, by construction, to reproduce the spectral function, and hence the Mott insulator. Now, so far, everything was exact. I was just showing this illustration to tell you that indeed this spectral potential in principle is able to also obtain a Mott insulator. What about approximations? In principle, we could use the same starting point, that is the definition of the effective potential, and we could make approximations to these exact relations. And this is what is normally done in the framework of optimized effective potential of DFT. An approximation, in this case, is the fact that we can linearize this equation. So we can replace G by G of Q everywhere, including the functional dependence of the self-energy. Why we have to do so? Because otherwise, this is not a constructed definition of the this effective potential. Because if we know already the Green's function, then we don't need to use the effective potential anymore. So in order to use in practice, we have to make approximations. And this in particular is an approximation that doesn't require the knowledge of the full Green's function, or is its diagonal, which is the quantity that we want to calculate. So if we linearize, then we can obtain the effective potential and we can use it. And this is indeed done in the case of DFT. If the self-energy is the Fock operator, so if there is only the exchange part, and this is the Shamschluter equation for the exchange correlation potential. So V of Q is just V of V XC of R. Then this is the exact exchange approximation that has been derived, for example, in this work, and this is used in DFT. The problem is that still this optimized effective potential way of deriving approximation is computationally very intensive. You see that you need to calculate all these complicated ingredients, and then you have to solve this equation that you have to solve together with the solution of the Kohn-Sham equations. So what about the spectral potential itself? Well, the idea is that instead of using OEP, again, we can get inspired by the LDA and by this idea of using auxiliary words and model words. The idea would be to import the information from the homogeneous electron gas by using a particular connection here that we have to design. Here it's where all the effort in deriving approximations is going to, in such a way that we can obtain directly the spectral potential without going through complicated expressions like OEP. And this was indeed done quite empirically by Marco Vanzini in his PhD thesis. And we have derived, just as a proof of concept, an empirical connector that is able, using this spectral potential, and this approximation is known as we have named it as dynamical local connector approximation, to reproduce a given self-energy. In this case, it was a calculation with hybrids. But all this was very empirical, and I'm not going to spend too much time on this. This was just to show that, in principle, this is possible. And we have applied it to just three materials: sodium, argon, and silicon. In any case, if you want to know more about the spectral potential, I suggest you to have a look at the PhD thesis of Marco Vanzini. And in this paper, we have applied the spectral potential to a toy model that is the Hubbard-Dimer. I would like now to make a connection. And yes?
About, I don't know, 10 minutes plus questions afterwards.
Okay, perfect. Okay. I would like to make a very quick connection then with dynamical mean field theory and the spectral potential, and to see which are the analogies and the differences. And the point is that in dynamical mean field theory, which is a framework that is focused on correlating materials, we start from an Hamiltonian, that is the Hubbard Hamiltonian, and we are interested in the local Green's function. In the case of the spectral potential, we are just interested in the local spectral function. This is a local Green's function that is, for example, the on-site Green's function, and typically this is defined in an orbital space. So this would be the diagonal in this orbital space. So also in this case, we have to introduce an auxiliary word where we have a self-energy that in principle is not known. And then we need to approximate this self-energy of this auxiliary word. And in the case of DMFT, we introduce a different model that is the Anderson impurity model, which we can solve. And from this model, we can obtain the local Green's function. And then we can connect the model and auxiliary word by asking that the local Green's function of the Anderson impurity model is equal to the local Green's function. And then we can obtain the auxiliary self-energy by making an approximation that is very close to the LDA, which is we assume that the functional dependence of the self-energy is just through this local Green's function. This is the approximation of single-site DMFT. Now, the remark I would like to make here is the fact that this is very costly, because in DMFT, every time one has to recalculate from scratch the Anderson impurity model. So we don't profit, as in the LDA, from a calculation that has been done once and forever by someone else for us. So there is some improvement that we can do here. I will just say that auxiliary systems are not always possible, And a counterexample is the one of the reduced density matrix functional theory. I will skip this in the interest of time. And I will go to the last aspect, which is the fact that we have introduced this scheme, and we have introduced the LDA, which is an approximation. And the approximation is such that we use as a connector the local density. But we would like to ask the question and to answer the question whether we can make this connection between the model word and the auxiliary word exact in such a way that we obtain the exact exchange correlation potential. And this is pretty general, so I will introduce this in a general way. I assume that I am interested in a quantity that I call Q that is dependent on X and is also a function of F. This can be an effective potential or of an auxiliary word or on an observable. And now I assume that I can calculate the same quantity in the model that depends on a parameter P, and it will be in general a different function that I call Q tilde of P. Now I'm asking the question, which is the parameter of the model such that the model is giving us the same quantity that I am interested in. This is possible if the two functions share the same values, of course. If it is so, I can answer to this question by a simple inversion of this function, if the inversion is possible. So the parameter P of the model such that Q and Q tilde are equal is just given by this expression, where I have just to invert this function here. And note that this P is now a function of X. It's different for any different F, and it's a function of F. This is what we call the connector. This parameter of the model is the connector such that the two quantities of the model and the real world are the same. If I put this connector in this function, I obtain the quantity I'm interested in. Now, so far, we have gained nothing because all this is exact, but it's useless so far because we have to invert this expression and we still need the quantity of interest that we don't want to calculate directly. So the point is that we can approximate this exact expression. And the idea is that we approximate both the function in the model and the real function, the real quantity that we want to calculate, in such a way that we benefit from error cancellation. And then we have an approximate connector that we use in the model to calculate the quantity Q that we are interested in. Why all this is advantages with respect to the calculation of the quantity of interest directly? For two reasons. The first one is that normally we directly approximate the quantity of interest. And this result is good if the approximation is good, and it's bad if the approximation is bad. In the case of the connector, we benefit from error cancelling, from the fact that here we can have this error cancelling between the quantity that we approximate directly, and the quantity in the model system. So the result is good if the approximation is still good, even if the model is bad. And the result is good if the model is good, even if the approximation is bad, because in this case, we make the same error in the model and in the real system, and there is error cancelling, and the result is still good. And the second point that is very important is that we can now calculate the model once and forever. We can store the results, and then, as in the case of the LDA, we just have to read the result from the model, and we don't have to recalculate every time the model we are interested in. I will just conclude with the example of the exchange and correlation potential, which was our starting example. In this case, we are interested in the Kohn-Sham exchange and correlation potential that is a function of R and a function of the density. And we have the homogeneous electron gas where we have this function of the homogeneous density. In the case of LDA, the connector is just the local density, and we have the local density approximation for the exchange correlation potential because we import the result from the gas through the density, the local density. In the case of the connector, we make this connection exact in principle, and we design a connector that is a functional of the density, and it's different for each point. And an important point is that when we insert this connector here, what we obtain is that we have a non-local density function. Meaning that if I need the exchange correlation potential at the position R, I don't connect to the gas with the local density, but with a different density, a density that is obtained in this way. Now, this was abstract so far. I have also to choose an approximation. An approximation, for example, that we studied is a linearization around an homogeneous density. So what we have to do, we have to approximate both this and this. We have to approximate both sides here. So we approximate the exact Kohn-Sham potential, and we approximate also the potential in the homogeneous electron gas. And then we solve for the connector. We solve this equation for the connector. And you see that in this way, you obtain a connector that is a non-local functional of the density, contrary to the LDA. And then we have tested this on different systems. And for slowly varying density, we obtain the LDA. And for rapidly varying density, instead, the connector tends to a mean density approximation. It becomes a non-local function of the density. And okay, then we have calculated the density in the case of silicon, and with using this connector approximation. And the important point for us, and this is a comparison with the accurate quantum Monte Carlo results that I've shown you at the beginning. The important message for us is that the connector approximation is improving with respect to the LDA. Both of them are sharing the same model, which is the homogeneous electron gas, and we don't increase the computational cost. So for silicon, this is very good. And actually, the connector is the best approximation here. In the case of sodium chloride, the connector is still is not now the best among all these approximations. And the reason is that sodium chloride is farther away from the homogeneous electron gas than silicon. So the homogeneous electron gas is a better model for silicon than for sodium chloride, but still the connector is improving with respect to the LDA, which is the goal of all this. If you want to know more, this is the reference. Otherwise, I suggest you to have a look at the PhD thesis of Ayub, who did all this work. And I will conclude here. I will skip all the part about TDFT. If you are interested, we can discuss this. And the conclusion is the fact, the summary is the fact that I have introduced the concept of auxiliary systems that target specific quantities, specific observables. And this has allowed me to see the different frameworks in the same way. And I have discussed briefly the connector theory that is connecting model and auxiliary systems that is useful to design systematic approximations. And the last message I would like to make here again is the fact that accurate benchmarks and also accurate results for models are needed. And all this we are doing because we think that the idea of calculating something once in a model, storing it and sharing it, and then using these connections between model and real world is very important. It's something that we can benefit of, and it's a very interesting idea that was derived, was suggested, was put forward in the 60s by Kohn-Sham. But we can now profit from, for example, machine learning. Instead of calculating many different materials and then use machine learning on these different realizations of the same calculations, we could use machine learning to learn pieces of information from simplified systems that we call model. And this would lead us to a different way of material designs, in such a way that we assemble different pieces of Lego, starting from calculations that are done and stored and shared. and preferably done by someone else, right? Okay, and with this, I would like to thank you for your attention, and I will be very happy to take your questions.
Okay, sorry, I was delayed in unmuting. Thanks a lot, Matteo. I think this was very, very interesting and very much on the spot for what concerns the overall discussion we have during these days. So I've seen there are a couple of questions that we may want to discuss loud. Let me go quickly to Slack. One question is from Edward Linscott. Do you have an idea of what scope there is within the MFT framework to reuse solutions of the Anderson impurity model? Does connector theory have anything to say about this?
Yes. Indeed, we know colleagues that are working in the MFT, and we have suggested already several times this idea that we should avoid to calculate the model every time we do a DMFT calculation. Of course, this is much more complicated than in the case of LDA and Concham, because the Anderson impurity model is not characterized by a single parameter, and the quantity of interest is not just a simple function. But we could use nowadays machine learning to tabulate and to interpolate this large amount of information in such a way that we could profit from a calculation done once and forever. So this is one side, and the second side is, of course, the fact that the connector theory is also suggesting ways of going immediately beyond LDA, and also we can think about generalizing these ideas of the connection between the upper word and the auxiliary word. So in particular on this side, we have some ideas, and we think that we can work on this.
Thanks.
The other idea, I think, is open for contributions for those that are expert in machine learning, for example. I think it would be very valuable. So
thanks. There's a second question that is about error cancelling within the connector theory. Question is it more or less universal, or is it system and approximation dependent? Perhaps I don't know if you have your own arguments or numerical evidences of this.
Yes, so the error cancellation is general, of course. The point is that it depends on how the model, so this error cancelling is good if the model is close to the real system. If the model is far from the real system, then this error cancelling is not good, in the sense that the two errors would behave in a different way. So we would not profit from this error cancelling. So far in all the applications of this connector theory that we have not applied only to Concham, exchange correlation potential, we have profit from this. But if the question is whether we can set this in a mathematical framework, this is of course a very interesting question. And since this is quite abstract, it's also difficult to say, and I don't have the general answer to this.
Okay. Time permitting, I have a comment myself, or actually a question that is, especially at first, when talking about exact solutions or reference result, you were mentioning quantum Monte Carlo. And in principle, many body perturbation theories somehow also would come with this promise of being hierarchical and improvable in a controlled way, though experience seems to say that is not that easy, actually. So I just wanted to ask your own perspective on, so is it possible to use many body perturbation theory also besides quantum Monte Carlo in a controllable way, or?
Yes, this is part of our job to go beyond GW, for example,
Exactly.
but it's also very difficult and computationally very expensive. And actually, one of our goals is to get rid of GW and self-energies, even though I'm working most of the time with the Green's function theory. The point is indeed that it's very difficult to find approximations that are at the same time accurate and computationally cheap. So yes, in principle, we could go beyond GW, but we have the risk that that the calculations are complicated. Then I think it's more promising, rather than to calculate, to do improvement on the side of the real world, to do improvements on the side of the model world. In particular, I was underlying here the fact that quantum Monte Carlo so far cannot produce observables that are related to excited states. So in this case, I think that, for example, using many body perturbation theory could be useful, and it's interesting. And just to answer briefly to this, to address briefly this point, we have done so in the case of the Bethe-Salpeter equation. So it's the idea is to use the homogeneous electron gas in order to obtain exchange and correlation kernels in TDFT, same spirit. And in the case of the homogeneous electron gas, let's say the optical properties cannot be calculated with the quantum Monte Carlo. So the idea was to use the Bethe-Salpeter equation, that is the state of the art for the calculation of optical properties and in general of response function. The bad news is that the Bethe-Salpeter equation in the standard approximation is not good in the homogeneous electron gas. The good news is that then this allows us to go beyond the standard approximations, and it's a field of research itself. And so we obtain good results by including vertex corrections beyond the standard Bethe-Salpeter equation. This is not published yet, but it's going to be submitted soon. So also this is interesting per se. But I think that we should, in this case, spend effort rather on the side of the model with respect to the real system, because it's computationally very intensive.
Thanks a lot, Matteo. I think with this we have probably concluded a bit the the Q&A part. So
thank you very much.
And both our speakers of this late afternoon session, Renata Vencovitz and Matteo Gatti.